The following presentation is brought to you by Discovery Education, leading the world of digital and video learning. Discovery Education. Connect to a world of learning.
When you eat an ice cream cone, you have two things, the ice cream and the cone. Both those parts can be described by their shapes. In mathematics, the shape of a cone is called, well, a cone. And the ice cream is usually scooped into something shaped like a ball or sphere, which helps it fit inside the cone. Since you can hold the cone to eat the ice cream, that means it's three-dimensional. It takes up space, from side to side, up and down, plus towards and away from you. But some things are flat or plane shapes, essentially taking up only two dimensions, like these flags, the pages of a book, this ocean map, these kites, or even a painting hanging on your wall. If you lay these flat and look at them directly from the side, they don't have much height. In fact, they're so flat, you can basically ignore the height and look at only the length and width. That makes them two-dimensional. But whether two- or three-dimensional, many simple shapes have specific properties and names. Let's look at some examples. Bicycle wheels keep you rolling because they have boundaries in the shape of circles. A circle is a set of points all the same distance from one point, called the center. Circles are plane shapes, or two-dimensional. They don't have any straight sides. But other shapes do have straight sides. If they do not have any curved sides, we call them polygons. Every triangle has three corners and three sides. No more, no less. In fact, the prefix tri means three. And then there's the rest of the word. Angle or corner, triangle. What about squares, rectangles, rhombuses, trapezoids, and parallelograms? All these shapes have four straight sides. That means they're quadrilaterals. Let's take that word apart. Quadra, that means four. Lateral, that means side. Okay, what about shapes with more than four sides? Home plate. It looks different from the other three bases because it has five sides. Its shape is a pentagon. Penta means five, and gon refers to the angles. It has five angles inside it, and also five sides. 1, 2, 3, 4, 5. Stop signs. You see these eight-sided shapes at many street intersections. Its geometric name is octagon. Octa means eight. It has 8 inside angles and 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. If you take the words apart, you'll often find great clues to help you remember all about polygons. Poly means many, so polygons have many angles, formed when many sides intersect. Every quadrilateral has 4 sides and 4 corners, meaning 4 angles where the sides come together, but that doesn't mean that quadrilaterals are all the same. Let's start with this window. It's in the shape of a rectangle. See? 4 straight sides, 4 right angles. Opposite sides are parallel and the same length. Now, look at the panes in the window. They have 4 straight sides and 4 right angles, but all the sides are the same length. That means it's a special type of rectangle called a square. Snake and fish scales look almost square. They still have 4 straight sides, all the same length. A shape with 4 straight sides the same length is called a rhombus. A square is one type of rhombus, with right angles. A rhombus is a type of parallelogram, and so are rectangles and squares. In a parallelogram, opposite sides are always the same length and parallel. But some quadrilaterals have only one pair of parallel sides. These are called trapezoids. Quadrilaterals without any parallel sides are neither parallelograms nor trapezoids. All these shapes have 4 sides and 4 corners, and that makes them all quadrilaterals. This diagram shows how some members of the quadrilateral family are related. Some are trapezoids, some are parallelograms of various types, including rectangles, rhombuses, and squares. But quadrilaterals without any parallel sides are neither parallelograms nor trapezoids. Built over 4,000 years ago, the Great Pyramids of Egypt were tombs for Egyptian pharaohs. They're also the most famous example of a three-dimensional shape, the square-based pyramid, one type of rectangle-based pyramid. What if the base of the pyramid is a more elongated rectangle? That would still be a rectangle-based pyramid. All pyramids are three-dimensional, with a polygon for a base and flat triangular faces that all meet in a common point, or vertex. Let's look at some other three-dimensional shapes. Oranges, baseballs, soccer balls, bowling balls, and golf balls. In geometry, these are all in the shape of spheres. A sphere is a three-dimensional figure with points all the same distance from a central point. The back part of some trucks and boxes are in the form of different three-dimensional shapes, called prisms, whether rectangular or square. These sandcastles are made up of a variety of three-dimensional shapes. That means any object that has depth, length, and height.
People throughout history have honored some geometric shapes because people thought the shapes had power. The pyramid is such a shape. The ancient Egyptians used pyramids as special places to bury their rulers after they died. Hindus believe that pyramids have the power to preserve things placed inside them. Other scholars think that the Egyptian pyramid shape was meant to represent the sun's rays, or a way for the dead king's soul to reach the heavens. Some scholars think that the Egyptian pyramids may have symbolized a mound from which the world was created. Whatever the reason for pyramids being built, scholars are fascinated with how they were constructed, not an easy task. Regardless of claims of spiritual power in geometric shapes, they are designed and built into all sorts of everyday places and things. Some are obvious, like the circular and triangular shapes in this house. And some are not so obvious, like the trapezoid and rhombus shapes in the design of this hotel. These shapes, along with all other geometric shapes, have certain properties. Angles, numbers of sides or faces, the type of or lack of symmetry, and dimensionality. Let's take a closer look. Architects throughout the ages have incorporated geometry into the frameworks of the buildings they design. Triangles and parallelograms are among the most obvious two-dimensional shapes used in design, as seen in roof designs, windows, and entranceways. But there are more subtly expressed shapes too, like this trapezoid. Frank Lloyd Wright was a famous architect of the 20th century. His use of geometric shapes in his architectural designs is legendary and has inspired countless architects to follow in his footsteps. These buildings are just a few examples. Notice the shapes and angles that are incorporated into the design. We see triangles, squares, rectangles, trapezoids, and parallelograms. The angles are obvious as well, acute, obtuse, and right angles. Let's review the different types of angles. This angle is a right angle, also known as a square angle, which measures exactly 90 degrees. A square has this type of angle. An acute angle, highlighted here, is any angle smaller than a right angle, or less than 90 degrees. It's found in triangles, trapezoids, parallelograms, and many other shapes. Obtuse angles are greater than a right angle, that is, more than 90 degrees, as seen here. Although this castle was built centuries ago, it also exhibits various geometric shapes. Can you spot them? In the roof lines alone, there are triangles, rectangles, squares, and trapezoids with various sized angles. See them? The mosaics and design of the castle's interior are particularly complex, filled with a diversity of shapes and angles. What were the ancient Egyptians thinking when they built the pyramids? Why didn't they build a huge cube to bury their kings? It's probably because the ancient Egyptians believed there was more to this pyramid design than meets the eye. These Egyptian pyramids are triangular-looking, three-dimensional objects, consisting of 4 triangular faces and a square base. Each of the 4 triangular-shaped sides slopes up toward a single point where they all meet. Each side of the Great Pyramid at Giza is a flat surface at an angle of 51.5 degrees from the horizontal base, all the way up to the top point. The ancient workers that built this pyramid started at the bottom and worked their way up, making precise angles at every level. A tiny error at the bottom could lead to a very large mismatch by the time they reached the top. The large limestone and granite blocks used to build the Great Pyramids weigh about 2.5 tons each. Imagine how many men it must have taken to move each block. The geometric shape of those large blocks is called a prism. Prisms are three-dimensional figures that have congruent sides that are parallelograms. Here, the sides are rectangles, which are a kind of parallelogram. Inspired by the ancient Egyptians, by their own beliefs, or simply by the geometric features of pyramids, people build homes, offices, and even museums based on that simple, presumably powerful shape. A shape has bilateral symmetry when one half is a mirror image of the other half. The measurements of each mirrored part is the same, but often the shapes are not superimposable. One cannot be fit exactly on the other. Symmetry exists all around us and tends to be related to our perception of beauty. If the image is two-dimensional, then this is called a line of symmetry. In a three-dimensional shape, it's referred to as a plane of symmetry. Bilateral symmetry can be seen in the delicate wings of a butterfly. Like the butterfly, most animals in our world have symmetrical features, like the fluke of this humpback whale, or the body of this manta ray, each side an almost mirror image of its opposite side. In human form, rough symmetry can be seen in the way your eyes, ears, cheekbones, and other features are aligned. In fact, most of the human body contains symmetrical properties. 2 arms, 2 hands, 2 legs, 2 feet, each side opposing the other. Mathematically speaking, a line down the center of a plane geometric shape or a plane dividing a three-dimensional shape down the middle will reveal its symmetry. Some rectangles become 2 squares when bisected down the center. A line corner to corner in a square makes a symmetrical pair of triangles. A regular hexagon can be divided into 2 trapezoids by a line from one corner through the hexagon's center to the opposite corner. Now you can see how each half of a bilaterally symmetrical shape is a mirror image of its other half.
Geometric shapes can be changed in many ways to make other shapes. One way is subdividing. Here's a square. A line segment from one vertex to the opposite vertex divides it into two triangles. Here's a regular hexagon. A line segment connecting opposite vertices divides it into two trapezoids. You can also make smaller versions of the same shape by subdividing some shapes. For example, a line segment from the right angle vertex of this isosceles right triangle to the middle of the opposite side divides it into two smaller triangles similar to the original one. Architects and interior designers subdivide a floor plan of a house to figure out where to put walls to make separate rooms. Geometric shapes can also be combined to create other shapes. Combine two triangles along a side of the same length, and what do you get? A quadrilateral. And if the triangles have particular shapes, then a rectangle is formed. Architectural designs often involve combining geometric shapes to make other, and at times, more complex shapes. Changing or distorting a shape can create other shapes in an endless number of ways. A circle can be stretched out to form an ellipse. A square tilted to one side is another kind of rhombus. A trapezoid can be made from a rectangle by making one side shorter than its opposite side. Let's look at other ways we can divide, combine, and change shapes to make other shapes. Architects are professional shape dividers. Here's an example from an unusual house. Starting with a simple shape like a circle or ellipse, an architect brings an empty space to life. Gardeners, like architects, often subdivide a space too. They create smaller sections for each type of plant. The original plot is often divided into smaller shapes, often rectangles. Landscape architects create more exotic gardens, like this one, with pools and fountains in its design. Let's see what shapes we can find that have been subdivided into other shapes. Notice the overall shape of these pools? It's a rectangle, but it's been subdivided into smaller rectangles, and from this perspective, the subdivided shapes appear as trapezoids. Although unintended, the photographic image of the reflection in this pool contains the five-sided shape of a pentagon. It can be subdivided into a trapezoid and a triangle. Subdividing shapes can be done in an infinite variety of ways. Architects throughout the ages have thought of innovative ways not only to divide spaces, but to combine geometric shapes in their work, creating unique and world-renowned designs. They've also found ways to combine two-dimensional shapes to form three-dimensional structures. These domes are two examples of combining different shapes in different ways to achieve similar structures. This geodesic dome is built by combining triangles. And this mosque in Istanbul, Turkey, has a dome composed of trapezoids. This hotel displays various geometric shapes and angles. Here, various geometric shapes are all combined to make stunning artwork. The overall shape of the artwork is a rectangle, but smaller rectangles, squares, and trapezoids all combine to make a variety of shapes and designs. Many shapes can be seen as they combine to make the square ceiling design. A large octagon in the center, some triangles around it, some hexagons around those, some squares, and some trapezoids. And notice how within these shapes some combine to make other shapes. For example, the octagon combined with four of the triangles makes a large square. Combine it with the other four triangles and you get a different large square. Combine a small square with two hexagons, a triangle, and two trapezoids, and you get a pentagon. By combining simple geometric shapes, other and more complex shapes can be built, with possibilities that are endless. Designers have always manipulated shapes to create new and innovative designs. Tilting shapes like a square to make a rhombus, or stretching a circle to make an ellipse, are just a couple of examples of shape-shifting. Can you think of other ways shapes are changed to make another shape? How about the U.S. flag? This stunt skydiver is parachuting with the U.S. flag trailing below him. He has to hit his mark exactly so the men on the ground can catch the flag before it touches the ground. Nice catch. Now the men can fold it up. The flag of the USA is made in the shape of a rectangle, but when folded correctly at the end of the day, that rectangle becomes a triangle. Another example of changing one geometric shape into another is the Japanese art form of paper folding, called origami. A simple square or rectangular piece of paper is transformed by creasing, pleating, and folding it into shapes, making boxes, frogs, clowns, birds, and other shapes. Combining, subdividing, and changing basic shapes transforms them into other shapes or combinations of shapes, and each can be done in a seemingly infinite variety of ways.
Photography is an art that involves close attention to detail and special attention to the subjects in the photograph. We can describe and compare figures in photographs by their shapes and sizes. In many photographs, the forms and their relationships help make the photo interesting.
Yeah, that's it. That's beautiful. Hold it. Great.
In geometry, figures with exactly the same shape and size are congruent. They could be superimposed exactly one on top of the other. Any measurement on one is exactly the same as the corresponding measurement on the other, including lengths of any straight sides and sizes of corresponding angles. These windows have congruent shapes. And so do these. They're rectangular, with all corresponding sides the exact same size. One of the methods photographers often use for composing a good photograph involves dividing the frame into congruent and similar shapes. On the rectangular shape of this picture, draw an imaginary line from one corner to its opposite. This creates two new shapes, triangles. They're congruent because they have the same shape, and they are the exact same size. We can also say they're similar. Now draw another line from a corner, perpendicular to the first diagonal line. This makes two more similar triangles. Similar forms have the same shape. All corresponding angles are the same, and the lengths of the corresponding sides in both forms have the same relationship. Congruent shapes are always similar because corresponding sides have the same relationship to one another. They're equal. Photographers often place their subjects where the lines intersect. Let's look at more examples using congruent and similar forms.
Pushing down a little.
Ever wonder why interesting places are called tourist attractions? Because they attract tourists. Usually lots of them. And where there are tourists, you can bet there are cameras. Let's see if we can find congruent forms of objects they're photographing and in the photos themselves. Do you see congruent forms in this ancient pyramid? Look at these stones. Believe it or not, this stone is 5 feet wide and 5 feet tall. and so is this one. Both have sides that meet to form 90-degree angles. So, their faces are the same size, and they're also the same shape. That means they have congruent forms. Notice that the triangular faces of the pyramids are also congruent. Their corresponding angles are the same, and the corresponding sides are the same length. Now let's suppose a tourist photographs the pyramid and gets 2 copies of the photo exactly the same size. The images of the pyramids in both photographs are congruent. We can also say that the photographs themselves have congruent forms. They have the same shape and size. These photographers might look like tourists, but they're actually scientists studying a group of apes. In everyday language, the mother ape and her baby are similar. They're the same species, although one is younger and smaller. But in geometry, we can't call them similar because their proportions are different. For example, the baby ape's head is a greater portion of the whole body than the mother's is. Similar forms have the same shape, with all corresponding angles the same, but are not necessarily the same size. However, in order for them to be similar, they do have to have the same proportions, like these 2 photos. Each side of the large one is twice as long as the corresponding side of the small one. Of course, the images in 2 identical photos, printed at different sizes, still have similar forms. All proportions in them are the same because they're the same photo image. The ape's head in one is the same proportion to its whole body as in the other. And an ape and its mirror image, same everything, congruent, and also similar. One of the world's most popular tourist destinations is Paris, France. The magnificence of its many old buildings and bridges plays a part in its popularity. And the congruence and similarity of its structures' architecture has everything to do with their beauty. The Pont Neuf was the first stone bridge built in Paris and took 30 years to complete. Its arches are congruent. They have the exact same shape and size, which means they are also similar. In fact, all circular shapes are similar to one another, and so are all half-circular shapes. But they're not congruent if they're different sizes. One of the largest and most famous museums in the world, the Louvre, only became more of an attraction when it opened its newly designed glass pyramid entrance in 1989. Its 739 rhombus-shaped panes of glass are congruent and similar. They have the same shape and size, and their angles are the same. We can say the same about its larger sides or faces. We can also find similar forms within each face. This triangle is similar to the larger one. Both have the same shape, of course, and though one is smaller than the other, their angles are the same, and their corresponding sides have the same relationship. Each side of the smaller triangle is 14/17 the size of the larger triangle's corresponding side, as indicated by the numbers of window panes. Also, the non-overlapping sides are parallel, making the corresponding non-overlapping angles the same. Look around and you're likely to see congruent and similar shapes everywhere.
Have you ever seen a real live dinosaur or dragon? You haven't, because scientists have determined that dinosaurs lived millions of years ago. And you know that dragons only flared their nostrils and breathed fire in fairy tales. But that doesn't stop animators from trying to bring both creatures to life on film. Using computer animation and motion geometry, artists take dinosaurs and dragons from science and fiction to the screen.
Go behind the scenes to see how the biggest special in Animal Planet history was created.
They transform geometric shapes using translations or slides, moving a shape from one location to another without changing its orientation, size, or shape. Rotations or turns, making the figure rotate about a single point or axis along a circle. And reflections or flips, reflecting one shape to the other side to produce its mirror image. These transformations help artists build the creatures on screen with depth and the sense of motion, making the animals and their worlds look real.
We set out to make dragons as convincing as possible.
Let's have a look. Dragons flapping their wings and wagging their tails. Dinosaurs running, fighting, and craning their necks. Does watching all this make you wonder how'd they do that? Creating such detailed moving images on a computer can be broken down to simple geometric shapes and their transformations. How does this dinosaur walk across the earth? The artist uses a translation to create the illusion of movement by shifting a shape from one location to another without changing its shape, size, or orientation. See? The shape, size, and orientation don't change, just the position. The transformation makes it look as though the dinosaur is walking. The same concept applies to the footprints it leaves behind. The artist has created a pattern of footprints by translating each one forward, from one location to the next, without changing its shape, size, or orientation. We can replace the footprints with triangles. See how the shape's location changes and nothing else? These transformations reinforce our perception of the dinosaur's motion, and before we know it, have us wrapped up in an animated world that seems real. Another technique of motion geometry that artists and their creatures really couldn't do without is called a rotation or a turn. These dragons, courting one another by free-falling with feet clasped together, look like they're rotating in the air. That's because artists move the shapes that make up the dragons about an axis, creating the perception that they're actually spinning. See? Each simple shape rotates along a circle around the axis. In geometry, a rotation changes the orientation of a shape, but not its size. A flip probably makes you think of this kind of flip. But the term flip in geometry refers to producing a shape's mirror image, its reflection. In the world of computer animation, artists flip geometric shapes all the time. Looking at this early computer creation of a dinosaur, you can see that one side is the mirror image of the other. The shapes don't change, but their location and orientation do. They've been reflected to the other side. Can you visualize the reflection used to create this dragon's wings? Look closely. One can be made using the mirror image of the other, the one shape reflected over to the other side. Let's flip or make reflections of these shapes. Look at each reflection. The shape's form and size is the same. We just changed its location and its orientation by flipping it over. But notice that the square and circle still look the same. That's because they have a flip within their shape. See? We can cut them in half, and the halves are mirror images. They're symmetrical. Animators use these transitions all the time.
So once all these elements are combined, hopefully you will believe that you are seeing real dragons.
Realistic dragons and real-looking dinosaurs, thanks to motion geometry.
Train tracks often stretch for long distances in a straight line. Lots of things around us have the form of straight lines or segments of them. In geometry, a line is a collection of points that extend straight in both directions endlessly. A line segment is a part of a line. It's the shortest path between the start and end point. Skyscrapers often have forms with line segments that extend high up into the sky. Floors also have shapes with straight line segments. A ray is a part of a line that has one endpoint and continues endlessly in one direction away from that point. An angle is formed when two rays or line segments have a common endpoint. Here, the sun appears to have light rays forming angles. Most windows have angles as well. The two sides of this window form a right angle where they join. A right angle is the angle of a square corner. It has a measurement of 90 degrees. Let's look at other characteristics of lines and angles. Parallel lines are lines on the same plane that never come together or intersect. Parallel lines can be seen on the edges of straight roads and in the traffic traveling on them, and in train tracks. Highways are divided into lanes by parallel lines to help guide the traffic. Swimming pools also have parallel lane dividers to help guide the swimmers. Even if we could stretch out the lines forever, they would never intersect. Parallel lines can also be found in smaller structures, like this porch, as well as this fence. Lots of musical instruments also have parallel or nearly parallel lines. Look at these piano strings. Cello strings are very nearly parallel too, as are the strings on a guitar. Perpendicular lines form equal angles all the way around. On this chessboard, we can see where all the lines meet. They form square 90-degree angles. Many tiled floors also have perpendicular lines, forming right angles where they intersect. This traffic sign has a 90-degree angle. And this monument has many perpendicular lines. Let's highlight where the lines meet to form right angles. There are 8 right angles. Intersecting lines cross at a single point. Train tracks run parallel, but they intersect when they cross another set of tracks in a rail yard. Note how the intersecting tracks are like intersecting lines. The panes on this window form a series of intersecting lines. Just like parts of this bridge, take a look. Where lines intersect, angles are formed. The angles on the bridge are less than 90 degrees. They're called acute angles. Look at all the acute angles just on the near side of this bridge. Angles greater than 90 degrees are obtuse angles. There are 3 types of angles: acute, obtuse, and right angles. The top section of this building is in the shape of a trapezoid. It has 4 angles inside the shape, where edges of the building come together. 2 of these angles are acute, and 2 of them are obtuse. These sides of the trapezoid are parallel, so if extended endlessly, they would not intersect, but here they stop.
Maps can be a key to discovering and learning about a city, a country, or even the world. The view looking down from a helicopter looks like a map. This is Tokyo, the capital of Japan. The city's area is about 240 square miles, but a map that big would make no sense. A map is a much smaller representation showing the main features, as though you see it from far above. Many maps are printed on a large sheet of paper. This is a computer-generated aerial view of New York City. When we look at a map of New York City, we see the lines and figures representing the subway system, streets, bridges, parks, and key landmarks. Maps help us figure out where we are in relationship to key features and how to get from place to place. Outdoor enthusiasts often use maps to find their way on mountain trails and through dense forest. Archaeologists use maps to help them navigate through the jungle in search of ruins. Sometimes they draw their own maps to mark important locations of ruins. Later, this scientist will compare the map he has drawn to the map created on his computer. Meteorologists study and collect information about weather. They often use maps to locate and track the movement of storms. The maps help them make accurate predictions. Let's look at other examples of maps and how they represent what's in the world. Maps are full of potentially useful information, like how far one location is from another. This biologist is measuring the distance between 2 places on the map and then comparing it to the map's scale. A map's scale is used to show how distances on the map relate to real distances on Earth. Australia is a country and a continent, almost as big as the United States. This is a map of the country, and this is the map's scale. For a large place like Australia, the scale represents real-life distances that are very long, compared to the map's short distances. Map scales sometimes have 2 scales in one. The distance may be represented in both miles and in kilometers. Let's use the scale to help us figure out the distance in miles between Sydney and Brisbane. One way to measure the distance between 2 cities on a map is to use a ruler. We can measure the distance on the map using the ruler and then compare the distance to the map scale. On the scale, 1 inch equals 600 miles. Our measurement is slightly longer than 1 inch. That means the distance between Sydney and Brisbane is a little over 600 miles. Maps are helpful for understanding distances between places. You may have noticed that model planes are much smaller than real planes. Model planes are like 3-dimensional maps. They're a convenient size to include major features of the thing they represent, and they show the relationships of those features. This is a map of the entire planet Earth. Notice that a map of something as large as Earth can be as small as the size of a poster board. Many maps represent smaller areas of the Earth as well, like the small islands in Hawaii or a small city like Kitty Hawk, North Carolina. Drawings can even be made to represent spaces as small as a bedroom. These girls have made a scale drawing of how they want their room to be rearranged. It's a kind of a map. Have you ever drawn a picture of a cell? We can create maps or diagrams of things that are so small they can only be seen with a microscope. This is a picture of a cell. The diagram of the cell is much larger than the real-life cell it represents. Its scale has very tiny distances, too small even to see without a microscope, represented by the much larger distances in the diagram. Like other maps, it includes the important parts of the thing it represents and their relationships. We can create maps of things of any size. Maps can represent something as gigantic as planet Earth or something as tiny as microscopic cells. What all maps have in common is a clear representation of the relationship between different things. This team is hiking in an adventure race. The race requires plenty of endurance and the ability to read maps. Their biggest challenge is climbing up and down this mountain peak. This map will help them get information about the distance they must travel. First, measure the distance from point 19 to point 21 with a ruler. The distance on the ruler is 1 inch. Now, let's compare that distance to the map scale, which indicates 1 inch is 5 miles. So the distance according to the map is 5 miles. After they reach the top, they'll descend using the same trail. To figure out the total distance they'll be hiking as measured from above, we can multiply 5 times 2. 5 times 2 equals 10. Their total hike is 10 miles as though measured from above. Now notice one other thing. This map does not show the added distance due to their climb up and down. Their hike will actually be somewhat longer than 10 miles, measured along the ground. From the relationships shown on maps and the scale of the map, information about distances can be determined between things or locations represented on the map.